The chain complex is a sequence of modules like this: C4, C3, C2, C1, C0, and maps between them. So these maps are given by arrows. So out of every module C3, there is an arrow coming out which is delta 3. Out of C2, an arrow is coming out which is delta 2, and the arrow is also going into C2. So simple structure. There's an important condition here. Kernel contains the image. So kernel of the map going out of C0 contains image of the map coming into it. So you have kernel of delta 0. This contains image of delta 1. Similarly at C1, map going out is delta 1. So kernel of delta 1, it contains image of delta 2. Similarly at C2, kernel of delta 2, it contains image of delta 3. So say you have an element x here. You apply delta 2 to it, you get delta 2x here. But this delta 2x, because image of delta 2 lies in the kernel of delta 1, if you apply delta 1 to it, it gets mapped to 0. So composition of two maps like this is 0. So delta square is 0. So you take any element, you first apply delta to it, then again delta to it. So here we have applied delta 2 and delta 1. You get delta square as 0. So generally you do not write indices under these maps, delta 1, delta 2, delta 3, because you already have indices under this. So once you mention this complex as C3, then you automatically know the map going out of it is delta 3 and map coming into it is delta 4. So let us see this more pictorially. So you have C2 represented by this big oval and C3 is represented by this big oval. So part of C2 gets mapped to kernel. So delta 2 is acting on this entire oval and part of it is getting mapped to the kernel, that is part of it is getting mapped to 0. So say this portion right here is getting mapped to 0. So we are going to shade this portion. So this portion gets mapped to 0. But image of delta 3 lies within the kernel of delta 2. So this entire module here gets mapped inside the kernel. It gets mapped somewhere inside here, say like this. So we have colored the image of delta 3 right here in green, and kernel of delta 2 is this entire shaded portion. Now let us modulo out the image part. If you take out the image, whatever is left, we will color that in, say, magenta color. So this is precisely the homology. So notice that again this entire thing is getting mapped to 0. So homology is just part of the kernel when you modulo out the image. So homology at C2, which you will write as H2, this will be kernel of delta 2 and then you modulo out image of delta 3. So in general, obviously the formula would be Hi would be kernel of arrow going out of it, delta I over image of arrow coming into it, delta I plus 1. So in C1 you will have kernel of delta 1 modulo image of delta 2. At C4 you will have kernel of delta 4 modulo image of delta 5. And this is precisely what the homology is. So the question is, why do we even bother about homology? So the reason is the same as in fundamental groups. So if the homology groups are different, so different homology groups would imply spaces are different. The topological spaces are different. The implication in the opposite direction does not hold. So different spaces could have same homology groups, but if the homology groups are different, the spaces are different. And that is primary criteria or the objective of algebraic topology. In fundamental groups also we passed from the category of topological spaces to groups. Here also we are passing from category of topological spaces to groups. Now let us compute some examples. So the first example will be of a circle S1. So we are not telling right now how this complex associates with the circle. So this will come later. So but for now, just take on faith that with this S1 there is a complex associated which looks like this. So this complex would have integers in place C0 and C1, and everywhere else it is 0. So the first map delta 0 is just nothing but multiplication by 0. The second map delta 1 is also multiplication by 0. So first notice that C2 is just 0, C3 is just 0, C4, C5, so on are just 0. So homology group at C2 will be just 0. You have nothing here. Now homology group at C0, so that will be H0. So what is the kernel of the map? So delta 0 is nothing but multiplication by 0. So kernel means this entire Z is getting mapped to 0. So kernel is integers over what is the image coming from this map. So delta 1 is also multiplication by 0. So the image is just 0. So what you get H0 is just integers. Similarly for H1, the map given to us delta 1 is multiplication by 0. So this entire Z is getting mapped to 0. So this entire Z is in the kernel. So you have Z and nothing is coming out from here, just 0 is coming. So over 0. So you are modulo outing 0. So you will just get integers. Now we talk about sphere Sn. So the complex looks like this. This delta 0 is multiplication by 0. You have in C0 you have integers. C1 is 0, C2 is 0, so on. In the part Cn you have integers again. And all these maps are multiplication by 0 and 0 is coming in. So again the same case. So this is precisely the same. 0 is coming in. You just have integers here. Integers, you modulo out 0, just get integers. For Hn, for here, you again have entire Z is in the kernel because you're multiplying by 0. And you modulo out 0 is coming in 0. So this doesn't make any difference. And for all other I, it is just 0. So here I greater or equal to 2, it is 0. Here for all I not equal to 0 or n, it is just 0. It's just 0 are sitting there. Now we talk about another space, S1 wedge with S2. So this appears in many contexts. In fact, we have a complete lecture on avatars of this space. We computed this fundamental group of this space using Van Kampen theorem. You should probably see that lecture in elementary homotopy theory. But for this space, again, there are a large number of maps, but all maps are multiplication by 0. So by now you would have guessed the group. At C0 you have integers, at C1 you have integers, at C2 you have integers. So for H0, it is just multiplication by 0. So entire Z is in the kernel over 0. Here delta 1 multiplication by 0. So you have integers over 0 because 0 is coming in. Image is 0. Again for H2 you have integers. Entire integers are getting mapped to 0, but 0 is coming in. So if you modulo out 0, nothing changes. So we are keeping this as such. So these are very simple spaces to compute. We'll see more spaces in which this multiplication will not be 0. But you can easily see that, for H0, it will always be the case that you will have C0 over image of delta 1 because C0 is always getting mapped to 0. So kernel of delta 0 is always C0. Entire C0 is getting mapped to 0. But for other spaces, we have to think a little. So this was very simple examples. Let's compute more examples. We now discuss two important spaces, RPN and CPN. So RPN and CPN have these complexes associated with them. So C0 consists of integers in both of them. In C1, you have integers in RPN and 0 in CPN. In C2, integers in both of them. In C3, integers here, 0 here. C4, integers here, integers here. So first we will deal with CPN because structure looks very simple. It's just multiplication by 0. So you can see H0 corresponds to here. So entire Z gets mapped to 0 and nothing is coming into it. So H0 is just integers. What about h1? h1 is just 0 map, so you have 0. h2 again has integers into it, but 0 is coming into it. So entire z is getting mapped to 0, but image is just 0. So this is integers. And again you will have h3, which will be 0. h4, this would be integers, and so on. So obviously for even you have integers, and h odd you have 0, because the structure keeps going like this. So you keep changing and it will just be like this. We will have integers in even places and 0 in odd places. Similarly, this structure here. So here we are taking n as 5 in our example, but you can extend it inductively. It will look like this only. So first notice that first map is multiplication by 0, and 0 is coming into it. These two are multiplication by 0. So h0 is just integers. Modulo out 0, which is coming from here, doesn't matter. h1. So entire integers are going to 0. But what is coming in? You are multiplying this by 2. So 2z is coming in. So h2. So h2 will sit right here. So let us compute h2 here. What is going out? You're doing multiplication by 2. So that means this is an injective map. So kernel is just 0. So kernel of delta 2 is just 0. So this map is 0. You don't really care about the image, because no matter what you write in the denominator, it's just going to be 0, because kernel is 0, since this map is injective. What about here? h3. What is the kernel? The kernel is integers, because entire integers is going to 0. And then you modulo out this multiplied by 2z, because that's the image which is coming in. Now here you have h4. What is the kernel? So kernel is just 0, because you're multiplying by 2, so it's an injective map. So you have 0 here. Doesn't matter what is coming in here. So again, now h5. So if you have it depends, what is coming here. If the complex ends here, then 0 is coming in here. So if 0 is coming in here, then you have just integers, because you're multiplying by 0. But if complex doesn't end here, that is, this n is 6 or so, then obviously you don't have a 0 here. You in fact would have integers here. So if you would have integers here, then you would multiply by 2, and then you will get z by 2z in case you have integers here. That is point number 6. So it depends upon where the complex ends, but it will just move on inductively. So again, we have not discussed how you obtain this complex from here. That how do you get this complex? This we have not discussed yet. So this will come in later. But if you're given a complex like this, you can compute the groups, the homology groups. And now the homology groups are different for these two spaces. So you say RPN and CPN are different. Now the torus and Klein bottle have these complexes associated with them. So this is the complex for torus, and this is the complex for Klein bottle. So in space C0, both have integers. C1 is also the same, and C2 is always the same. Everything looks the same except the maps right here, here and here. All of the maps are same. So for h0, for both of them, it would be integers, because integers are getting mapped to 0 and nothing is coming. This map is multiplication by 0. This map is multiplication by 0. So z modulo 0, just give you z. Now for this part, h2 here. Now for h2 here, z is getting mapped to 0. So you have integers, but nothing is coming from here, 0. So this will just be integers. On the other hand, for here, h2 would be injective map. This is multiplication by 2. So the only thing which is in the kernel of this map is 0. So h2 is 0. So you have 0 here and integers here. So this immediately shows that torus and Klein are not the same. So let us compute the h1 groups. So here again h1 is easy, because it is just integer plus integer is going to 0, and nothing is coming from here. So this will be just integer plus integer, because the kernel of the map contains this entire thing, and the image here is just 0. Whereas on this side you have 2z coming in. This entire thing, because of multiplication by 0, is going to 0. So you have, this is the kernel. So kernel is this, and the image is 2z. So you write this as like this. So one of the element would be z by 2z, and z direct sum with z by 2z. So this is associated with CW complex. So notice that delta complex will give you a different chain complex, but the homology groups will be exactly the same. So these chain complexes are corresponding to CW complexes. Now focus on the chain complex of the torus. So this chain complex is also given by the space S2 wedge with S1 wedge with S1. So the homology groups for these two space, torus and this space, are the same, but these two spaces are not same.